This is like where we left off last time, right? Talking about comparing the distributions, and a couple of things I wanted to hit. Again, this is the two distributions, histograms of the distributions of data we got from two separate random variables. The question was, are those distributions actually different? Okay, so we do that. Then what we do is we generate like, we talked about the null hypothesis, and I believe this is called the null distribution too, by the way, where you create a distribution of the like dumb luck. It's the dumb luck distribution, right? If it doesn't matter, it shouldn't have mattered which group they were from. Therefore, if I assign them to any other group, it wouldn't have made a difference. So what is the dumb luck app? Like we could all see that like sometimes if everyone who had just by dumb luck, faster recovery time in one group versus another group, it's gonna, look quite different, even though it's just dumb luck, right? Like I could split the course in half and sort everyone by height, and I can be like, oh wow, like put all like the taller half over there and the other half over there, and then like, oh, therefore like the tall people must have come from something. No, it's just like whatever, dumb luck, right? This course doesn't have anything to do with height, right? So it's just dumb luck. That's what this is. It is not to be confused with the distributions of data of this. Also, what this is of is like the statistic we are trying to like learn about. For example, like if I want to know the average recovery time, so this would be like the difference in average recovery time. That's what it is. But I can make this whatever I want, right? I can make the statistic whatever. I could have done difference in median. It doesn't really matter. And then, of course, we say, well, there's our dumb luck. This is what we actually observed. So how many of those, out of all of them, would have been that number or more by dumb luck? That's the likelihood of us getting it. If, of course, we did every single permutation, we would have a very precise number. But realistically, like I was saying in this example, there's like times 10 to the 29. Okay, we're not going to do all of them. But if we do a sufficiently large number, we're going to get, it'll be pretty darn accurate, right? Anyone in here know what the central limit theorem is? No? Yeah, it doesn't matter. It is kind of important. So like, if you take sufficiently large samples of anything, the distribution is going to start to look like a normal distribution, by the way. Yeah. All right. I did mention, though, at the end, like permutation tests, like it's very algorithm heavy, right? Like this is the process, right? If I were to think like, how do you calculate this? It's an algorithm, right? Shuffle, recalculate, right? I immediately think like, okay, I need like a for loop. But something like a t-test, for example, is you just pop it into an equation and you get a p-value like that, right? So this is nice and quick and dirty, where a permutation test is it's going to be thorough, but it's going to take a while. Mann-Whitney U is also kind of algorithmic-y, and a lot of that comes down to the fact that like with this one, it's like parametric, right? We make assumptions of like normal distribution of data, so we can like skip some steps, kinda, right? Where when you have non-parametric things, a lot of the non-parametric things tend to be more like algorithmic, but that's not overly important right now. But the permutation test is like definitively showing you, oh, that's what the p-value means. Okay, the probability of getting this observation by dumb luck is, well, how many of this were better? That's like what the p-value is, right? If the p-value is very small, the probability of getting like these distributions by dumb luck, if it's a really high number, well then chances are the distributions are pretty similar, okay? All right, now I also may have given the wrong impression at the end, right? Where I said, okay, SciPy stats, SciPy, stats, t-test, right? If you go here, there's like, oh, okay, here's your t-test, A, B, boom, right? If I scroll down here, it'll probably have an example, right? My goodness, right? There you go. I've just got two random data things, and I do t-test, boom, there you go, you get our statistic in the p-value. Wonderful, right? Great, cool, easy peasy, right? It's like a line of code, t-test. Similarly with like Man-Whitney U. Right? You just give it an X and a Y. Boom, you've got your, you know, you get your answer. Wonderful, right? Permutation test, there's more steps. But actually, there is something like this already in here. But there's a key difference because permutation test is like more flexible. You also have to give it, like you give it the data, except you give it like a pair of information now, not two like separate lists or something, right? You give it the data, but you also have to give it like a function of the statistic that you want to compare. So like in our example, I could have used this, give it the data, and I would have given like a function called, like I would give it the function like mean there, right? Or mean difference or something, right? Yeah. And if we scroll down here, there will be like an example, right? We've got two things, the data, the statistic. What is the statistic function? Does it show us? Yeah, the mean difference. Great. There, a mean difference is the statistic. Very common one that you would use. But you could use anything here if you really wanted. But mean difference is the statistic. And then so when we go down here, permutation test, you give it the pair of data. Give it the statistic. Here, like it's setting some of the optional parameters, right? The default ones will be fine for our needs. And then there you go. Oh, yeah, great, cool. Wonderful. Neat, right? Neat. So the reason I was showing you this is I don't want to give the wrong impression that like, oh, well, the permutation test is so much harder to do than like a t-test. No, it's actually pretty straightforward still with SciPy, right? You just, whatever. It might take a second, though, if it's going to do like a million iterations, of course. All right. Any questions before we move on? All right. So we're going to talk about multi-objective problems. I think only you did that for assignment 1, right? And what were the two objectives? So everyone did like a single objective function that was minimize the Hamiltonian cycle length, right? But yours, if you did the vehicle routing, it's minimize that and also like minimize the number of vehicles or something, right? Yeah. So there are two things to minimize. Okay. So, and you might say like, well, how does that work, right? Like, like why would more vehicles use less distance? Well, think about it, right? Like if I have, see if I can come up with a simple example here, right? Oh no, it's dead. How did that happen? Oh, I missed. I'll get it later, don't worry. I'm so embarrassed. Okay, so like, what's the distance here? Like, let's say this is like X and this is Y, right? With one vehicle, we would have like X plus Y plus Y. Is this a good example, X? I don't know if it'll work with this simple of example. 2X plus 2Y, right? That's the total distance, right? If we did 1, it would still be the same total distance, just with two vehicles. I would need more of a more complex example for this to make sense. But maybe you get the idea that like, well, by increasing the number of vehicles, we could reduce the total distance that is traveled by our vehicles, but at the cost of additional vehicles. So, yeah, right? That's just an example, but like anything, the example I'm going to show is like, well, I want to buy a house, but I also want my house to be like as big as possible for as little amount of price, right? Usually, if you're buying a house, you're going to consider more things, like is it big enough for your needs? What's the amenities nearby, right? a lot of decisions we make are going to be based on some form of like utility analysis, right? Like when you're given a set of options, you have to kind of like pick, well, which one do I like the most? And when you add more things to consider for each option, it gets complicated, right? But we all kind of have a systematic way of like picking what you would like, right? Like if I gave you options of meals, right? Well, you could have like chicken and beans or beef and broccoli or something. Which one would you pick, right? Well, maybe you really like broccoli and you really like chicken, but you don't love it. How are you going to pick, right? So you have to have a way to kind of calculate all this type of stuff. We all just kind of do it in our heads, right? But as soon as we want to start doing it algorithmically, we're going to need to have some systematic way of going about doing these calculations. For the most part, all problems looked at have been single objective. It's not uncommon to have multi-objectives. So like consider buying a house. You want a low price, you want at least 4 bedrooms, you want it to have a small commute distance, I want it to be nice, close to nice and close to the amenities I want, and I want it to look nice, right? Some of these things are rather subjective, like style, the amenities I care about. Like I might be next to like the fanciest pet parlor in the world, but I just don't care, right? Like, so obviously some of these are subjective, and some complement each other. So you might have some like, well, if chances are like, if it's close to like all of the amenities you like, it's probably also going to be like, maybe like in like a densely populated area where your work might likely be, right? So chances are, okay, if it's close enough to amenities, it's also close to your work, you know. Maybe that might not be universally true, right? But you can envision it, that situation. And some of them are going to be like in conflict, right? At least 4 bedrooms, okay. If you compare 4 bedrooms to 3 bedroom, you know, generally the bigger the house, the more bedrooms, the bigger the house, the bigger the price, right? And if it's close to amenities, the bigger the price. All of this is to say, sometimes you have multiple objectives that complement each other. And that's actually a rather straightforward situation, right? It's, oh, great, they always complement each other, so great. But sometimes they are in conflict with one another, and that makes it complicated because how do we pick what we like? Did anyone do the multi-objective for GP? Which one?
I did for breast cancer.
Okay, yeah. Okay. All right, so like here we go. Now, here's something I want to emphasize about this plot. Okay? All of these data points are houses, price, and like size. Okay? Now, take a moment and look at these. Just take a moment and look at this plot and like what do you see here? What can you observe? What conclusions can you make? Like what do you see in this plot? Take a moment and try to understand what it's trying to tell you. Yeah, that's what we want, right? But I also the point here is big houses cost more. So what do I value more, a lower price or a bigger house, right? How do I pick one? When you look at this plot, are there any points that you're like, yes, pick that one?
Just any of the points on the line?
Yeah. Well, let's take a step back. Why any points on that line? Well, look. Consider this house. It's kind of expensive. It's not too big. And look, here's something that's less expensive and bigger. Why would I pick this thing if this existed, right? Sure, you could compare like, oh, this one to this one. Which one should I pick? I don't know, right? Like, Sure, this one's cheaper, but it's small. This one's more expensive, but it's bigger. I don't know, but I can definitely see like, no, this one's better, right? Definitely pick this one, right? Why? Well, it's better than this in both like directions, right? I don't have to give up anything. If I'm here to here, I have to give something up, right? Like, okay, I give up the price for a bigger home. But like what do I want? Okay, great. That's hard to answer when it comes to multi-objective functions. This, though, is pretty straightforward. It's bigger and cheaper. Awesome. Similarly here, look, this is bigger and cheaper, right? So it turns out there are these things called, well, a lot of this comes from economics, actually, and we will come back to that. Okay, we're going to come back to that aspect of it. We're going to start actually with the much simpler version of dealing with multi-objective problems. This is a very simple strategy. Simple doesn't mean not effective. It is effective. It's very effective, but it does kind of require, there's like a bit of a catch, okay? And if you did multi-objective for genetic programming with deep, then you definitely would have dealt with this. It's what I talked about before. It's a weighted sum, right? So that's like saying, okay, if I want to minimize the price, okay, let's call it price plus size, right? Maybe let's not even put plus here because it could get confusing about how we combine them to create a single value. But the point is, okay, how much do I care about the size versus how much do I care about the price? Also, there's like a normalization aspect of this as well. We kind of talked about this before, where price is probably going to be on the order of like hundreds of thousands, right? Size is going to be on the order of like a couple thousand, right? So if you were to just kind of like add these two things together, their scale is way out of whack, right? So like anything that reduces price is going to dominate that like sum of the fitness values, right? Because like, oh, 500,000 to 400,000. The size of the house went from 2,000 to 1,500. That makes no difference in this grand scheme of things here, right? So we've got this normalization issue, but that's easy. You just multiply this by a couple thousand, so by 100, I don't know, right? Pick a number, make them comparable. Great, okay, cool. All right, so now they're like normalized. Okay, great. And I can do a weighted sum of, this is like, yeah, this is the weight, right? You see what I mean? Yeah. So it's like normalized enough that like improvements will matter one way or the other. But there's also another aspect of the weighting I need to think about. It's, well, how much do I care about one over the other? Do I want to favor, like imagine these were perfectly normalized, okay? It's going to mean 1 unit of improvement here is equal to 1 unit of improvement here, right? But maybe I really don't want to pay a lot, okay? So yes, I care about this, but maybe I'll make price like be weighted a little bit more, right? Like, yes, I do want a reduction in price to be worth more to me. This is good and bad. What's good about it is it gives you the flexibility to assign those weights. How much do you want to prefer one thing over another, right? That's awesome. But what's the downside? Downside. Well, the downside is you got to set these weights, right? So like, yeah, you got the flexibility to set those weights. How much do I care about price versus size really, right? there's not like some subjectiveness there, and I'm trying to quantify it. That's always quite tricky. We can agree that there exists some utility function that I'm using in my head, but I don't know what it is. All I know is that like, you know, I'll love the house when I see it, right? Like, do you see kind of what I mean? So like, yes, it's awesome I get to tune these things to get what I want, but also I have to tune these things in a way to get what I want, but what if I don't know how to tune them to get them in a way that I want? Ugh, right? It's a pickle. Do you see, right? Not a huge deal, right? But you know, it is an extra thing you need to do. This would be an example of scalarization. Scalarization is the process of scaling the various features to be optimized by combining them into a single value. It's basically a cheesy way to take a multi-objective problem and squeeze it into a single objective, right? It is an a priori process, meaning we need to make a decision about our scaling before we do it. Like, we gotta make this decision, all right? And scientists love using Latin to make themselves sound smart. The simplest thing, a weighted sum, all right? Given some number of features that I wanna like optimize, here I've got M, right? Each one's gonna have a weight, I add them together. Great, okay? Nothing particularly scary here, right? Now I will warn you, in practice, if you're doing something like a weighted sum, will it work? Yeah. But once this gets real, good luck, right? Like, yeah, good luck, okay? It's just gonna get too hairy. Too much is going on at once. Yeah, okay, basic math, great. You all know what a sum is. You should hopefully know what a weighted sum is. Have you ever calculated your final grade? You know what a weighted sum is, cool. All right, if one objective is more important than another, give it a stronger weight. Use negative weights to account for objectives that are to be minimized, maximized, and maybe like conflicting one another. Or invert it in some way. But again, weighted sums do not work well beyond 2 or 3 objectives. It's the way it is. And it's probably pretty obvious, right? Like, you're just you're trying to put too much information into a single value. You're trying to summarize, because think about it, right? When you have 3 values, that's very descriptive, right? These are the 3 things. You can even look at the weights. Those are the 3 things. But as soon as you add them together, you weight them and add them together, and you're putting it into a single value, you've lost all that like meaning, right? You don't know how much came from what, really. So like you've lost information. So, you know, whatever. Further, it's not always easy to assign weights, yeah, like I was saying. So any questions about weighted sum? There are other ways to go about doing it, but this is just like your standard easy peasy, up and running, you got something working. Cool? All right. Now, there's this idea of dominance, all right? And this goes to what you like pointed out, is everything on this line is good. Like, just take a moment and understand that. This is the best one in terms of price. That is also biggest. I can go bigger, but I'll lose the price. So along here, I've got a trade-off to make. But there's no option in here where like, well, I could have got something bigger and a better price. Okay? That's the point here. What's nice about this is when you're done, first of all, consider the fact that evolutionary computation is almost always like a population-based search. When you're done running your algorithm, you don't have one answer, you've got a population of answers, right? So you've got a suite of solutions. They're not all going to be good by virtue of the variation operators that took place on the previous generation, right? Like, that's going to happen, but a chunk of them are going to be good. Here is the idea of this dominant set. I could go to somebody, if you came to me and you said, I want to buy the biggest house for the smallest price, or maybe you've got a logistics company and you want to minimize the number of trucks used, maximize and minimize the total distance or something, right? Like, that's what's going on, right? And if I try to do a weighted sum, it's going to be really hard for me to determine the weights based on what you want, right? Right? Like, think of this as like an actual commercial endeavor. I am a logistics figure-outer contractor, okay? You come to me and you're like, okay, I want to do this, right? And I'm like, okay, great. How much do you care one over the other? And they're like, just make it better, right? So I go back and I'm like, okay, how do I assign these weights? Hard enough to assign the weights for something that like I want, let alone read someone else's mind, right? So it's always really tricky. This though, if I went to that person at the end and said, here is a set of options. One is not necessarily better than the other. In fact, they are, strictly speaking, not better than one another. They all have their own strengths and weaknesses. Anything you in here, you're not going to do better than anything in here. Okay? But now you get to look at this and be like, oh, I like that one. Do you see what I mean? So it won't give you an answer, but it'll give you the set of the best options because there is no best answer. That's the idea here. And it works really well with evolutionary computation by virtue of like the population base, right? Okay, so sometimes it's not possible to truly select the best. If one house has a lower price than another, then it's good. And if one house is bigger than the other, then it's good. But how does one compare price to size? It may be clear that some options are better or worse than others. So if a house is, let's go back. If a house is bigger and cheaper than another, then it's good. Okay? So what do we have here? In the above example, point A is better than B in both dimensions. This is a minimization one now, okay? I guess closer to here is better. All right? So A is better than B. Why? It's closer to this way in both directions. By the way, this also will work in 3 dimensions and so on and so on and so on, but in practice, you're not getting past 2 or 3 dimensions very effectively. It is what it is. All right, so A, we can clearly see A dominates B. It's better in both ways. Now, A and C, A is better than C in one dimension, but equal in another. Okay, but I'm willing to bet if I want something closest to here, which would you pick, A or C? A, right? All things being equal on that dimension, it's lower on that dimension, so I prefer it. So, A is worse than E in both dimensions, right? And then with D, well, it's difficult to compare, right? Like, yeah, it's better on this dimension, but worse on this dimension. You see? So really what we want to do is kind of like find these like fronts or dominant sets. Because you can actually go and be like, okay, look, A seems to dominate B and C, right? So they're in like a set. Because what's better, C or B? Hard to compare, right? So it's hard to compare. They're similarly good in the sense that, well, you win some, you lose some. But A is definitely better than those two, right? So it dominates those, but it doesn't dominate D because, it's kind of comparable. But E is better than that. So you can kind of see how you've got like these like frontiers of dominance. And that's kind of like going up to like this idea, okay? All right, so here one would say A dominates point B and C. Although A and C are equal along the x-axis, A is still better on the y-axis. Like you would always pick the one over the other. Thus, one would still choose A as, further, point A is dominated by point E. Cool. So that's kind of like how we're doing it. Solutions dominating, dominated. Pretty neat, right? This all comes from like economics. A lot of like cool stuff comes from economics. It kind of like sneaks in, I think. Right, okay, so yeah. Then we get to this idea of like Pareto sets. There's actually a lot of different names that people will use, but given a set of solutions S and some subset Q, a data point from S is non-dominated by the set D if no solution Y from D dominates X. Well, I'm going to show you what this means, don't worry. A set of non-dominant solutions N and C defines the Pareto optimal set. It's possible to create multiple Pareto sets by repeatedly applying the process on the set differences. Basically what you do is you go through and look for the ones that are dominated. Okay, these are dominated. Okay, you can remove them, do it again, dominated. Remove them, do it again, dominated. Remove it, do it again, and then, well, we're done. That's the last one. Okay, so it's kind of interesting. Because let's take a moment and imagine like we're minimizing along both axes, okay? With a weighted sum, we could just use the weighted sum as a fitness, right? But we could also like maybe use like which Pareto set it's in as like a fitness measure as well, right? In fact, like, yes, S1 is better than S2. Okay, all we really need for our fitness function is like there's like some ordering, okay? There's some gradient that we can follow. So we need like an ordering. So yeah, S1 is better than this. But again, you know, with selection, you don't always want to pick the best ones. But also consider the fact that, you know, there is differences within the set though, right? So always picking things from set 1, you're not necessarily going to just like, it's not really the same as picking the best candidate solution every time. Because consider the fact that like, yeah, there's going to be a lot of variation among candidate solutions that have the same fitness value. So there's a little bit of like a wiggle room and some room to play with in this thing, okay? Implementing this, so when comparing to a weighted sum, this is so much harder. Only because a weighted sum is hilariously trivial to do. Aside from like picking the weights, right? But this, there's a little bit more work you got to do it, but it's pretty easy to implement. I did it years ago, pretty easy peasy. I did it for an assignment. So like, yeah, you could definitely do it. Actually, I did it for the assignment where I did vehicle routing back in the day. Yeah, so yeah. Anyways, that's that idea. Pretty neat, right? Yeah, so evolutionary algorithm, Pareto style multi-objective optimization. Let me go back here. Did I miss something here? No, I guess not. So are there any questions about like how this is explained? Whoop, how I've explained this at all yet? Everyone's happy? All right. Okay, yeah. Okay, so since evolutionary algorithms are typically population-based, they work well with this like Pareto-style multi-objective optimization. It does work really well. They kind of go hand in hand. The population can be ranked into Pareto sets. The Pareto optimal set will contain all good solutions, and consider the issue where the weighted sum of selected weights for different quantities. Yeah, it's tricky with Pareto optimal set. There's no need to decide with weights. A set of solutions is presented at the end from which we can go, I want that one or that one or that one, right? At the very least, you can go like, I can do no wrong. I can't make an irrational decision with anything from this set. It may be difficult still to select though, but that's at least not something the algorithm is trying to figure out. It's for the user, right? So the key difference here, this is like a priori, where with the Pareto set, you could decide after the fact. Okay, here you go, you've like figured it out. These ones are all like your best options, like unequivocally your best options. Now you get to go and just use your gut, right? Because sometimes figuring out what the weight should be, which is based on your gut, you can't really, you know, right? Cool. Any other questions about this? Has anyone ever seen this name pop up anywhere else? Where?
In one of my machine learning,
Could be, yeah. In what context was it used?
when we're doing the analysis.
Yeah, was it for like multi-objective stuff? It was. How about anything else? Has anyone else heard the word? Yeah.
In economics.
Well, okay, yeah. But how was it explained there? Like what? Because what was it explained?
Call it like preferences or something.
Okay, that would probably be this. Yep. I'll warn you if you look this up. you will find, this is a classic problem with like machine learning people, and like if we steal things from like economics, we will start to give like different names to things. And so if it's a little like what, you can trust the like, yeah, right? It's bad with math too. Like the machine learning people, we went and changed all these words from the mathematicians, and the mathematicians got mad. It's a whole thing. Anybody else though heard Pareto?
Stats software I used before.
What did it have?
There's a chart.
Okay.
Look up just to double check.
Yeah. Has anyone ever heard of like the 80-20 rule? Yeah, that's like a Pareto thing too, right? The 80-20 rule. A Pareto principle, yeah, the 80-20 rule. It's like, it's this like principle, okay. Raise your hand if you've heard of the 80-20 rule. Yeah, yeah, okay. So the 80-20 rule is this basic principle that like, you can get 80% of the way with 20% of the work. To get the remaining 20% requires 80% of the work. And it's funny, I just use the example of like work, but like you can apply this principle to like everything. 20% of the people at St. FX do like 80% of the work. That's the way it is. Because everything follows this like 80-20 thing. That's not me jabbing St. FX, this is just the way it is. Everything like follows the 80-20 rule. The Pareto principle, yeah. 80% of the outcomes result from 20% of the cause. That's like the generalization of it. And it's like a shockingly correct like thing. If you live your life with this in mind, you will have a better life because you'll be able to make better decisions because you'll be able to be like, oh yeah. So like businesses, approximately 80% of the sales may come from 20% of the customers, or 80% of the income comes from 20% of the clients. Top 20% of the most reported bugs can eliminate 80% of the software errors, and so on. It's just this like trend is everywhere. So like, it is an empirically observable trend. It's not just like some like, oh yeah, some guy said. No, this is like a thing. It's pretty crazy. Yeah, and look, there's a whole wiki article on it, which is pretty neat, right? You can go read through it. Anyways, yeah. Cool. Right. Trying to think what else. So in economics, you may have so raise your hand if you've taken economics. So just you. What economics class was it that you took?
I took 101, 102, 201, and 301.
Okay.
A lot of micro.
Okay, so you would likely have seen this idea presented for like a more economics hat, but it's the same general idea. Shoot, and there was something else I was going to say about that, but I can't remember right now. What was it? I can't remember. Whatever. Anyways, questions? All right. PSO, particle swarm optimization. Now, before I get into this, let me clarify something. The assignment 3 is probably going to be most people find it to be like the easiest one. Assignment 3 is on PSO, okay? I also have like a working implementation that you can start yours from, of course. It tends to be like the easiest one, at least for implementing, and you'll see shortly how hilariously straightforward it is to implement. Now, that doesn't necessarily mean that understanding how it works is trivial, but if you do understand how it works, the implementation is a laugh. And that's not to say it's not effective. It certainly is. That's actually what we want, right? You want simple to implement algorithms to be effective. When I say simple, though, and easy to use, it's still a form of computational intelligence. This is still like a beefy algorithm that you don't want to have to use, but you could use. And I've known a lot of people that have actually done a lot of research in this area. I don't know, it just so happened that way. PSO has been really popular with them. It is a form of evolutionary computation that is probably the most, so like you have like evolutionary computation, which is like the biggest, broadest category. And then under that you have like evolutionary algorithms. Well, what's the difference? Well, like a GA is an evolutionary algorithm, okay? It's obviously still evolutionary computation. But then there's like another broad category called like swarm intelligence that fits under evolutionary computation. And you might not think like, oh, it's directly tied to where's the evolution here, right? It's different, but you could still see like the iterative process there and how it works. And if you try, it's not too hard to be like, wait, that's just like a GA, but you're doing it this way, right? So they are all still very connected. Yeah. So, all right, okay, I don't want to get distracted. I was getting distracted. For assignment 3, I don't have a due date set yet, but it's going to be like way late in the semester, right? It's going to be like the last Monday of the semester or something, right? And the reason for that is I don't want it conflicting too much with your project. So if your project is earlier, don't think about the PSO until you've got like everything kind of set, right? Or vice versa, if your project's later, well maybe do the PSO, so you've got the flexibility there. Another thing to note too is remember also, when it comes to your final grades, because someone was asking about this last time and I just wanted to clarify. It doesn't matter if you're a grad student or not either, it's going to be calculated the same way. Your final grade is the sum of your points, okay? And then it's not smushed in any way, and there's a total of 115 possible points in the class, meaning you could get 115, though the highest grade you can get is 99 still, so whatever, right? So that is like baked into the course to give you the flexibility of like, like you're not necessarily losing if you choose not to do something, if that makes sense, right? No, but you still have to do your final project, so that is required. Yeah, cool. All right. As, by the way, so we have like 2 topics left, okay? And we have like 1, 2, 3, 4 lectures left. So I'm probably going to finish the topics I wanted to before we get to the student lectures. I don't know what I'm going to do in that time yet. I haven't decided. Maybe I'll just kind of like show you some other cool things. I don't know. Or I don't know. I'll figure something out. However, we lost someone in the course. Someone dropped. And as a result, the first day is now also not filled as well. So again, I'm not sure what we'll do that day, but yeah, unless someone wants this time slot. Does anyone want this one? You can move. No? No one wants, no? All right, cool. All right. All right, PSO. It's a stochastic population-based optimization technique. And remember, stochastic is just a fancy way to say random without saying the word random. It's just like many other forms of evolutionary computation. And like I said a moment ago, if you squint, if you squint hard and look at the algorithm, you'll be like, wait, that's just a GA. Yeah, it is. But it's different, totally. But it's kind of like the same idea. It consists of particles that all act entirely independent from one another, except they are influenced by the particles around them. So each particle, they're independent, but they are affected by those other particles that are around them. And like, at least, I don't know how true this is, but at least like the story goes, the algorithm was kind of inspired by like somebody who was like watching like birds or something. They're like, what the hell? It's crazy, right? Right? And they were thinking like, think about how they're moving, right? Like they're all working. I think if you look, like I think there's like a predator bird. I think that's what's happening here, right there or something. And the other, they're like trying to avoid it. Yeah, so like the idea is each bird is making their own like independent decision, but those decisions are informed by what the other birds around them are doing. Okay? As a result, it appears that the flock is moving in like a coordinated way. But like there is no omnipotent force moving the birds like that. Everything is acting independently. But there's clearly some structure and pattern taking place, right? It's obvious, right? Like we've seen schools of fish that do the same thing, right? So like, yeah, okay, they're acting independently and it looks like there's something going on there. But at the end of the day, there's clearly some interesting patterns taking place. So PSO is particularly well designed to work with real number or floating point number optimization. All right? You're not going to use PSO for like TSP. You're just not. It's I don't even want to think about how or why, right? But you just don't want to use it like that. This is a perfect algorithm for floating point things. GAs, yeah, you can make them work with floating point problems, but use a better algorithm, a more appropriate algorithm for that, right? There are other forms of evolutionary computation that's good for real floating point numbers, right? But PSO is really good for that. It is hilariously simple to implement compared to other forms of evolutionary computation, which is saying something because we saw a GA, and a GA really wasn't too crazy, right? It has few hyperparameters, which is nice, especially if you compare it to like a GA. And it really is simple to extend and enhance. Although this is kind of like one of the big features and selling points of evolutionary computation as a whole is it's a framework. And you can do whatever the hell you want as long as you're working within that framework, right? So to say like, oh, it's simple to extend and enhance, yeah, all of the evolutionary algorithms are kind of like that. Particles, okay. A particle is like what's like analogous to like the bird or a fish in this particular thing. So what we do is we have a population of particles, and each of these particles are going to exist at some point in the search space, okay? I'm gonna, like, as an FYI, to make this as easy to wrap our head around, the problems that we're gonna solve are just like, here's some arbitrary mathematical function, find the smallest value that this function maps to, right? So like, if you're like, well, what are real world, like, we're not gonna talk about real world applications. Any floating point thing works as long as you have some way to measure where like they are. But imagine like, in the simplest form, if I have a one-dimensional problem, and here's like the f of x and x, right? The particles would exist somewhere along this x-axis, right? But like the search space looks like this, right? Right? So the particles will be like here, 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 right? And they just exist at some point in space. This should look familiar. This is kind of like a GA, right? Now this is a simplified version. It's just some one-dimensional function, but yeah, same idea. Like candidate solutions in a GA. Oh, what I just said. But unlike chromosomes, these particles don't have the traditional variation operators, mutation and crossover. They kind of have like mutation, but yeah, we'll see. And crossovers kind of worked in there some way, but again, we'll see. Instead, the particles have a propensity to more towards, that should say move towards, if someone wants to submit a pull request to fix that, to move towards areas that the particle likes. However, they're also influenced by the population of particles. They also have a propensity to move towards the areas of that the population likes. Okay, like if I like that, but everyone else is like heading over there, right? Like that's the idea. These particles also have like a momentum, like they've got like an inertia. So like think of like the bird flying. I want to go there, but everyone's going there, so maybe I should kind of like go that way too. That's like what we're aiming for here. In terms of optimization problems, each particle has a propensity to move towards the best area of the search space it has encountered, while having a propensity to move the best point in the search space that anyone in the population has encountered, right? So each particle has a velocity and an inertia. So here's an example. This is a two-dimensional problem, okay? 2D, and then like color, it's like a topographical map, right? This is a minimization problem, and you can kind of like get a sense of like depth, right? Right? And so these are the particles. They're all kind of starting. You can see it's like vector on where it's going. But there, it's finding the minimal, which looks like it's, I don't know, right here. See? It's kind of like how they're moving, okay? And at the end, I'll look and be like, well, which one is like closest to 0, right? And if you're thinking like, well, how do I know which, well, you would put this through. There'd be like some mathematical function, like a fitness function, that I can put these two dimensions into and it would spit out a value. And I've just picked the value that has the smallest number. That's what we're doing. And we're out of time, so we'll come back on Friday. Any questions? All righty. See y'all later.